Hey guys, it's part 2, just where I left off with the last one. I've got my software that I've written. Like I say, I had to learn a little bit, that's why it's taken so long. I needed to learn what the protocols were and the commands were to actually talk to my oscilloscope. Well, I've done that. I mean, my software, I'm going to publish it. It's not going to be on Microsoft Store because Microsoft Store has certain rules, and one of the rules is we can't have a dependency on an external DLL on somebody else's communication. The way it communicates with my my oscilloscope is using National Instruments Visa. Now I've put a link here to their website, and you can just download and install the runtime libraries. Let's just click that, and so basically on their site, that takes you to their site, and what you need to do is install this onto your machine. And what this is, it uses the I say the NI. It's a standard that a lot of digital machines use to communicate with each other, or with your software, or with your PC. It's like a standard dialogue, communication protocol or whatever, but you need something installed on your computer, like you do for my programs. For my programs need .NET. If you look on your computer, mine uses .NET Framework 4.8, which is standard on Windows 10 and 11, I think. But prior to that, you used to have to install .NET Framework for these programs to run, but now they're pretty standard. But it's similar to that. It's another set of libraries and protocols that lets you connect to a digital machine, really. Some sort of measuring equipment. That's what it is. Yeah, my brain's gone dead again. There's like a standard. It's provides for use in Ethernet, GPIB, serial, USB, and other types of instruments. So basically, let's see what it says here. Read more. There we go. There we go. Virtual Instrument Software Architecture, VISA. That's what VISA stands for. There we go. We need this. We need Virtual Instrument Software Architecture. It's a standard set of commands used to actually communicate with digital measuring equipment over USB, or over anything really, over serial, USB, and other types. And I don't know what maybe that's their own sort of connection, but you can even do it over Ethernet as well. Ethernet, whatever you like to call it, Ethernet. Yes, so that's what my program was, and I actually had to sort of swat up on this stuff. Then I could write I could communicate with my oscilloscope, and you can see that I can communicate. If I change this, actually there's two ways of communicating. There's screen and buffer. Now, what I want to do is actually show you the limitations. So the limitations is how much data I can capture. You can see that I can only capture so much. With USB serial, it's bloody fast, and from my data analyzer has trouble keeping up with it. The more you pay, the better equipment you can get, and so on. you know what it is. You're paying for basically memory and speed. But it's even worse with my oscilloscope, because I'm not actually streaming the data to my computer. I'm actually grabbing the data from the memory of the oscilloscope, and the memory of my oscilloscope is only so big. Basically, if I was using one channel, I would be able to use all the memory on one channel. Because I need two channels, the size of memory is halved, because it needs half the memory for one channel, half the memory from the other channel. So when you're buying oscilloscopes, and it's got this amount of memory, just remember, if you're using two probes, that is memory shared between two probes. I'm rambling again, aren't I? Anyway, so I've got it connected up here to my USB serial, and this is what we're getting. And the actual oh yeah, that's what I was going to do. I was going to actually zoom out a bit, so let me just alter my scope so I'm zoomed right out. And what I'm going to do is I'm just going to capture the screen, because the screen really shows up. So if I do another capture on my scope, and I've zoomed right out, and if I get that waveform from my scope, that's what it looks like. And if we zoom in, it looks like sod all, doesn't it? But actually that's because I've gone from a screen. So now if I get the full because the screen only is like 800 bits wide is the screen. It's 800 pixels wide, so that's what you get, 800 bits resolution. But if we go straight to the raw buffer, this is where you should always be getting your samples from. This is the same sample, so let's get that sample. And if we zoom out, we can see that we're now actually seeing some data, and you can see it's pretty crap. But I'm going to zoom out a bit more. And grab some more data. So now I'm actually getting, if I grab waveform, this is what that looks like on my scope. When we zoom in, we're only seeing one chunk. Oh, actually, I might not be talking to it. Let me just check. No, shit, no, I've closed the, like I said, you have to be actually talking to the USB for it to actually do some data. Let me start serial monitor up again. Right, so now let's just clear that. Yeah, so we're now talking to it. Let me just grab some more data. Yeah, that looks better. Right, if I zoom out there, now it's actually talking. So this is the amount of data I can grab. So we can zoom in and we can actually see the thing. But can you see it's pretty, really crap. Because the resolution of my oscilloscope it's only got so much memory to hold things. Let me just zoom out a touch more, see if I can grab a complete chunk. Right, so I'm just going to zoom out a bit more. Right, so now we can see several chunks here now, can't we? So we can see, so this receiving message from master hello is all in one of these blocks, so we can actually see that the whole message is in a block, because every time it does this, there's a gap. But when we zoom in, well, the resolution is pretty naff. And if what I can do now is, if I go channel 1 and channel 2 and try and filter this, we can have a look and see if we can actually filter it. And this is what the data logger was doing. Actually, I don't think that's too bad there. So because I can actually see what 1, 2, 3, yeah, that's like end of that one. So I'm going to zoom in one notch. So what I'm going to do, see if we can get just one of these chunks to fill the screen. Have I just redone that? No, I haven't. Yeah, that's better. Right, so if we get waveform, right, I've got it down to sort of one thing, so now let's just filter that. So what I'm doing, this is our actual, what I'm getting from my scope, and this is it filtered out. But you can still, it's still messy. So this is what I'm just trying to show with my scope, that it doesn't have enough memory to hold a decent resolution. Now if I zoom into the waveform and take a snapshot, like so, if I get closer in, let's just filter them, we can see now that we're actually getting some sort of actual square wave when we filter this. And what I've done is with the filter is the way it filters is, if you know what we got, someone named Schmitt can't say that, Schmitt Trigger, right? So you get devices with a Schmitt Trigger, and it wasn't invented with the chips that have the Schmitt Trigger. Schmitt Trigger actually was, he was examining nerves of the human body, and he was wondering why pulses down nerves sort of like only changed after a certain range, and that's where the Schmitt Trigger came in. It was actually from nerves. I mean, not bad, certain nerves actually pulsing inside the body. That's where it come from, and we just use the same word. Right, so yeah, so what I've got is I've got like I've written some software which acts like a Schmitt Trigger, and you can adjust the noise width. If you want to go into how Schmitt Trigger works, let me know, and I will do more information on adjustment here and how that does that, and I can go into it in a bit more detail. But basically, so that's what we do. So we've got that. I'll just minimize that now. Minimize that, and once we've got our wave, what we can do is we've got our capture. We can change that name there. What I'll do is I'll call that USB, and when we press this button, it actually converts this information here into a file that PulseView understands. So let's bring PulseView back. So we just open PulseView. And it's loading nothing in because what we've got is nothing. And I've made this application. It creates a folder in your I'll just open it up. So if we go to File, and you go to your documents, you'll find that once you've installed this software and you click this button, it'll create a folder called, in your documents folder, it'll create a folder called Tim's Scope to PulseView. And what we do is we go down and we go to choose all files, and we can see that we've got the USB one there which has been saved. It saves the USB, and we open that. Let's open that up. And so what we should be able to see is what we've got here at the bottom, the filtered wave. If we look here, we can see that we've got the filtered wave. And what we can do is we can select a protocol and go USB, and we choose this one, and we give it doesn't really matter as long as they're different. And there we go. we now can decode from our oscilloscope. Here's our USB information for each block. We look at it, and I have no clue what all this shit is, so yeah, we'll forget USB because I have no interest in USB serial. I just assume it does it. It's that stuff that's been done by cleverer people than I have. But anyway, so as long as you know that how it works, it's using a differential pair, and we can use this decoder here to decode this differential pair into some actual information. Right, so I'm done with USB, so get rid of that, delete that. What I'm going to do now is I am going to set it up on this I2C here, in USB anymore. What we're doing is we're going to do I2C, so I'll make a different file, I2C, and we'll capture out my waveform from my scope. Got them overlapping. Let me just separate them. Yeah, right, let's capture it again. Oh, hang about, I need to just redo a sample. Where did I think my thing's just locked up. Just give me a moment. Yeah, putting probes on this I2C tends to crash my little little processor on there. So, like I say, when I change stuff, it tends to lock up the microcontroller. So there we go. We've got some data, and what we can do is we can filter those, and we can look and we can see that we've got some nice. It's a lot slower as I2C, and but basically we've got data across the top, and we've got our clock underneath there, which you can see when we zoom in. There's our clock, and there's our data. So basically, well, it looks to me. Hang on, let's just zoom in. Yeah, it looks like we've got like 3 chunks of 3 bytes there. We'll have our address, and there's probably 2 bits of data following. We'll check that. So what we can do, we've filtered it. I'm going to save it under the I2C file, so I'll just save that. And what we can do is we can go in here and grab my I2C file. And there it is. That's what it looks like. And so now we can choose an I2C decoder. So we go I2C, and right, what you'll find is we've got that I2C there, which is probably what you have. But this is one I've rewritten. I've got ASCII as well, and the reason I've put ASCII, I'll look at that later. But we're not going to actually see it at the moment, see the ASCII, because what we're doing is we're just looking at the IC that goes to this display, and this display, there's no human words used to communicate between these. Everything is in hex, and basically it's a memory address, and then it's the it might be the memory command, and then it'll be a command following. So it'll be an address maybe of the screen, and it gives you an X and Y coordinate to give you on or off and what have you. Well, none of this data is going to make sense, but what we'll do is we'll choose this one, and the top one is data and the bottom one is clock. So you need to get these the right way around. So we've got our clock, which is the top one, and we've got our data. Sorry, no, the clock is the bottom one, and our data is the top one. So we got them the right way around, and forget about ASCII. We won't have ASCII on at the moment because basically there won't be any ASCII to read. It's all hex, and so we can see that we've got the address again going, and we've got the command byte and the data byte. And all this is coming from my oscilloscope. So my oscilloscope, I'm now able to decode a serial bus using my oscilloscope, using my little application that can get the data from my oscilloscope. We can filter it and send it onto here. Now you notice that I keep going to file and what have you, but if we're going to keep it on I2C, like I say, you can just see that all the data's here that we've got here. So all this data, you know, wherever we look at, we've got separate commands and data addresses filtered out, and that's what we've got here. So you can see that this is quite a bit of data we can capture with my oscilloscope. And this is what you're paying for, all this, but this is all free. But you know, when you buy a really fancy oscilloscope, this is what you're paying for, is all the decoding and the filtering. And if you and also there's some oscilloscopes with more than one data capture, but there are some oscilloscopes that do decode from the probes. So depending on what you want to do is whether you want an oscilloscope with probes or an oscilloscope that also has data capture, what is it, digital inputs as well. And usually those with digital inputs, you probably either get 8 or 16 extra inputs. And I'm rambling again. Yeah, so what I wanted to do is this, and then I wanted to show you I2C communicating from one Arduino to another. So if we go back to here, let me just set up what we've got. Alright, so what I've done now is I've now connected it to the I2C. So we've got the I2C bus here. So we've got the ground, the VCC, we've got the data, and we've got the clock wire here. Well, this wire is actually the same. This one's connected to the same wires here. So the same brown, red, orange and yellow, these are all connected to the same bus. I've just used a separate cable to aid. So what is happening is this Arduino is sending down this cable, which is this cable also, to this Arduino via I2C a message, and we can connect in there and see what that message is. So what we'll do is we'll take a snapshot of this with our, I've got my two probes from my oscilloscope. We'll get our my software is connected to the oscilloscope, and what we'll do is we'll grab the wave, and so that's the waveform that's been sent down these wires via I2C. We'll filter those two waveforms, and this is what we're actually seeing. So this is from my scope, is this top bit, and this is what we've filtered it to. And what I'm doing is we're going to the same I2C file, so let's just send it to the I2C file, and then we'll bring PulseView up. Because we're already connected to the I2C file, all we need to do is go reload, and I'll reload what we've just sent to that file. So let's just reload, and there we go. We can see that image. So that looks pretty much well, it looks exactly the same. We've got two short bits here, two short bits, a long bit and a short bit, and then we've got two shortish bits and another two shortish bits, then to very short and a short sort of thing, and very short there. So you can see that this is the data here that we've filtered and sent to the file. Now so in this pulse of I2C data from this Arduino going to this Arduino, where are we? Let's bring them back. Is here, and it's just continually sending that data. I could plug in the Arduino thing to see where it is, but the thing is I can actually read this one. So normally with PulseView you get the I2C filter, but I wanted it compatible with the Arduino and ASCII character set, and so I've rewritten it, and I've added this one here, which is hex plus ASCII. And what this does, if we go over here, is give us this extra line which adds the ASCII on. So what we can do now is we can actually read what it says. So we've got the address is going to which is here. I haven't got, I should have made that go all the way across. Anyway, never mind, because it's only reading 16. It's actually oh no, sorry. What am I talking about? Right, this is the address in hex. Hang on, let's just confirm that for you. Let's bring up the calculator. Oh, we're on programmer. So what is 10 in hex? Hex. If we go to decimal, so there's 10 in hex there, and what this does now is actually give you the decimal value, which is 16. So we can confirm that. That works nicely. It's this bottom line that I've actually added, and if we zoom out to see what the message says, so we've got our address and we've got the first letter here. I don't know if you can see that, but can you see that it's a H? I tell you what, now then, what's the zoom bit? Just give me a minute. Right, I'm just trying to think what. I'm sure it's Windows Plus. Yeah, Windows Plus. Oh, close that. Right, what I want to do is just want to yeah, so there we go. We can see that one's 16, and if we move across, we can see that the next one is H, and we've got hex 65, which is E, and then we've got hex 6C, which is L, and we've got another L, and we've got an O, and then we've got an exclamation mark. So basically what it's sending is a message saying hello. Can you see that there? It says hello now. Let me get rid of the zooming. I've forgotten how I do that. oh, hang on. No, I need to go up here. Hang on, find it. Shit. Where is it? It's over there. There we go. Close it. There we go. We're back to normal. Oh, you can see it there. I'm sure you can see it there. Can you see? Hello? That's what it's actually saying. And our decoder decodes this message. So that is our I2C. So our I2C has a clock and it has data, and it actually I2C is one-to-many, so it's not peer-to-peer like USB was, where it was one-to-one. I2C is one-to-many because it actually uses an address, and the second Arduino here is actually the device address hex 10 or decimal 16. So this is device 16, that's its address basically, or 10, which whether you want to do hexadecimal or you want to do decimal numbers. And that's what it's sending. So it comes down these two wires here, and what it does is the microcontroller reads that, and it knows that you've sent a message hello, and then the microcontroller then sends a message back out via the UART. So let me just bring Arduino back up. So if we bring Arduino back up, well, I just need to bring Arduino message here. So this is what it's doing. So this Arduino is receiving message from master hello, which we've seen down here. We've seen that message, it's hello and an apostrophe, and you can see that that's what this is actually. It's got the apostrophe at end, and it's sending that message. But the Arduino is sending this message to us that we're reading out via the UART, which then goes via this little chip here and to the serial, and then the serial, this reads the serial on COM19. So that serial is spitting out this message, and the serial is getting the message from the UART on this RX and TX. So let's have a look and see what's on that RX and TX and see what sort of waveform we get from RX and TX. It's not going to be the same as this, because UART relies on, it doesn't rely on a clock, it relies on a speed that you set it at, and it reads each data pulse at whatever speed you've told it to read the digits on the line. Let me set that up and hopefully it'll come to light. Alright, so I've got my probes, two probes on this cable here. This cable is plugged into my RX and TX on the Arduino, if you can see that. That's going to zoom in. Come on, zoom to something. Let's try and focus it. Oh, what have I pressed now? Oh, right, I focused on. Right, that's focused. There. Can we see TX and RX there now? There's TX and RX. Anyway, they're plugged in there. So I'm now connecting my probe to the UART, which is this, what is actually connected, which the actual microcontroller is sending the signal out to the serial through this chip here. So yeah, so we can now have a look at our serial lead, our UART, which is basically a single wire, but it's actually, there's two wires because we've got an out and an in. Oh, what's this doing open here as well? There, that's better. Right, yeah, so where's my my program? There's my program, and here's the PulseView. So what I'm going to do is going to get rid of the I2C decoder, because we're not decoding I2C, and what I'm going to call this a different file, because it's a UART signal. So I'm going to save it as UART, and let's get the signal. So this is the signal from my oscilloscope. Now you'll see that with all the data is on one line and there's no data on the other. Now this is a thing about the noise width, right? So I want to talk about noise. So that's what this slider does. Now this slider, if I well, this is held high at the moment. So let me just disconnect the low lead. I want to show you about noise when you're actually filtering, because the way my filter works, we need to eliminate noise basically. So what this program does, well, we can have a look and we can see the data there, and we can see that it's actually, oh no, sorry, I haven't filtered it yet, so let's just go. Yeah, so we're looking at the right thing. So that's our filter there, and you can see this is a nice dead line. But what I want, that is held high at the moment because there's nothing happening on the on the RX. We're not sending any serial in. we're only sending serial out. So this is basically a flat line, and the way things work is it's normally held high and pulled low to give you a message. So you can see that it's getting pulled low here, whereas before with I2C, no, it was same with I2C. Yeah, you've got pull-up resistors to hold it high, and then it's pulled low to give you a signal. Same thing with UART. But what I want to do, yeah, what was it? It was noise. We need to get rid of the noise, and well, how I have done. Can you see the noise here? Basically, if I just unplug that lead, let me just take that lead off. So it's low. So the signal will this blue one will drop low now. So let's just get waveform. There you can see that the signal has dropped low, and you can see that there's a load of noise on there. And if I filter that channel, you can see that the noise now is picked up, and it's converted to pulses. But we don't want that. What we need to do is we need to alter this this bandwidth here, noise width. So if I move that up there and filter, it's called me a frigging liar now, but I'm going to have to look at that, because that there was supposed to turn it off. It was only supposed to come on when I held it down here. Hang on. Right, yeah. We go up. What is the max and min there? Right, so channel 1. 128 to 131. Yeah, that's 3. So I only needed about 3. So if I turned it up to about 4, it should have filtered that out. And hang on, I'm going to have to come back to that. In fact, yeah, there's a bug in my software that should have filtered that out, and it hasn't. So I've cocked up basically. So let me just put that back on a high. Yeah. Well, actually, what I'm going to do is I'm going to swap the probes around, because I know that it worked on channel 2 before I did this. I just want to check that. I might have it on there. Yeah. I'm just going to swap leads around. Right. Well, I'll just leave it like that. Right. So let me just grab a waveform again. Let me just change the channel that we're let me just set my scope. I won't put you through this. Right, what I tried to show you before, I've swapped the channels around now, but basically what I've done is I've turned the noise down to 0, and what I do is when we filter it, it's going to filter all the noise out, which is all these little ripples, as actual pulses. But so when I filter channel 2, this is what we get. Basically we get pick up all the noise, and we actually filter and convert the noise to ons and off. So what this filter does, if we look at this noise here, channel 2, the high is 64 and the low is 61. So there's a difference between these high and low here of 3. So there's a peak of 3 here. This is 3 measurements basically. So what we need to do is filter out anything below 3 or 4 or maybe 5. Let's call it 5 and put it in the middle there. So now when I filter it, it now comes on a flat line, because it filters the noise out. And that's what it should have done before. I don't know why it didn't. Anyway, so there's our data coming in, and we filter that data as a clean. There's nothing coming on the yellow line on the channel 2, because channel 2 is transmit, and channel 1 is channel 2 is receive, RX line, and channel 1 is on the TX line, transmit line. And that's the thing with UART, you can actually transmit and receive at the same time, because you've got 2 serial lines. That's what I was trying to explain before, that these are 2 actual serial lines, but they're going in opposite directions. and the pulses are actually converted to digits using a time gate. You have a time gate between the pulses, and it works out whether it's high or low depending on the time it has been received. I hope that made sense. So I'm going to save it as UART, so we'll save it as UART, and then what we'll do now, because I've changed the file, we can't reload, I have to go to the UART file. That's where I've put it, on the UART, and there it is. There's our signal. We've got our transmit on the channel 1, and we've got the RX on the channel 2, and we're not receiving anything on channel 2, so that stays as a flat line basically. So what we need, but this protocol is a UART protocol, and so what we need is a UART decoder. So we go UART. Right, well. Yeah, UART. Right, so where was that? Oh, right, yeah. So, and again, as before, if you download PulseView and install it, you will get this UART converter here, this one here, and I've rewritten it again because I'm using an Arduino and I want to see what the actual character is without having to look it up, the hex number up. So we'll use this one, and of course you need to tell it what's what. So I think the receive line is 2 and the transmit line is 1, and there we go. So now we've set it up so we can actually see what it's actually sending here, and what it should be sending is let's bring up the Arduino again. What it should be sending is this. We've sent hello, and we looked at the I2C and it said it's sending hello. We've confirmed that. Then once this Arduino here has confirmed, has received hello, which is what we read on the I2C, it then sends a message out saying received message from master hello. So there's actually more being sent out than's being received in by the I2C. We're actually sending this message out, and you can see it's fairly long here, and we'll zoom in and have a look. So let's get at the beginning. Now I don't know if you can see that. Can you see R? I'll just do the zoom in and then zoom back out again, just so that it shows up on YouTube. So I think it was on that. Yeah. So yeah. So let's get to the beginning. I think that's the beginning. Yep, there. So we got the R, E, C, E, I, V, E, D, and a space, M-E-S, message, and then another space from master, and then we got colons, and then we got the actual message hello thing. So let me just try and zoom that out a bit. There we go. So there, that looks, there we go. I don't know why there's a gap here. I think that's an Arduino thing. It's a little thingamajiggy. I don't know, but yeah. But there you go. You can see received message. So we've now decoded the UART. Let's just get that back. I think I need to go up. Here we go. There we go. Back to normal. Yes. So we've decoded UART. If it was we were sending some traffic the other way, it would also do this. line as it decode this line here and see what we sent back. But because we're using a Arduino Nano, we're using this Arduino Nano and to send and receive, the message that is actually sent can be sent as ASCII, and we can actually decode it as an actual value. Right, so I think that's enough. I've showed you my thing. So basically what we're doing is we're using an oscilloscope to decode serial data on a serial bus without having to have a special oscilloscope that has this built in. Because if you want an oscilloscope that has this built in, basically it needs to have a lot of memory. It has to have the waveform convert, so it has to be able to convert the waveform to a nice clean digital thing, and then it needs the decoder. So what you're paying for on these more expensive machines is actually these decoders. This is what you're paying for. Is this, all this has to be written into the oscilloscope, so it can actually decode the thing, and it also needs to have the filter built in. I mean, it's all software. I mean, this is all can be done like I've done with the once it's been retrieved. I mean, the oscilloscope. This is what oscilloscopes were built for, was just getting a waveform. But for actually converting them, then you use a digital analyzer. But to save me digging out my digital analyzer when I'm just probing two serial lines, I find connecting this up is a lot easier and quicker, and I can still keep messing around with my my probes and my oscilloscope. I've only got the one machine connected up. I hope you found this interesting. I know I waffle on a bit and I'm very hard to explain things, but yeah, I still need to do what I hope to do is put the my program into a package where you can just install it and it does everything for you to install. Actually, at the moment I'm just running it through I'm just running it from Visual Studio, yeah, I'm still working on the thing, but it takes me a little while with writing code. I'm a very slow writer, so that's why it's been such a long time since my last video. But yeah, I just hope you found it quite interesting. Being able to do this with the digital oscilloscope, as long as it's got data out, that's what you need on the USB. I don't know. Oh yes, and my oscilloscope is Unity UTD 2102 CEX Plus. I don't know if this is going to work with others, but the protocols used to communicate with the oscilloscope are quite universal, so it may work with other scopes that have this have the ability to connect via USB. Yes, there we go. If you made it this far, thanks for watching and putting up with my ramble and stuff. I'll end it there because it's it's gone over an hour again, so I'll leave it there. Thanks for watching, guys.